let's talk about some prerequisites. Also, if my writing you don't understand, just say it out loud. I'll write it again because I know I have a problem there. Okay. I'll just say it out loud. Don't have a problem. Okay. Lovely. Okay, so let's talk about some prerequisites. Now, thinking about electromagnetic waves, what do you think? What kind of prerequisites does one would need in order to go ahead and study a subject like this? Well, one would need a sense of what electric fields are, what electric fields are, what magnetic fields are. So essentially, electrostatics and magnetostatics, and a bit of electrodynamics and magnetodynamics from the sense of fluxes, flow of magnetic fields. If there's a magnetic field flowing, if there's a certain loop that you have, certain amount of magnetic field is crossing it, then we know that current is essentially said to be set up, and if there is changing electric field, there's supposed to be a magnetic field that is set up. Um, yeah, so electrostatics, magnetostatics, all these things are prerequisites. So, remember to brush up on things like capacitors. Um, what else? You have these laws, lies, right? Ampere circuit laws, ampere's circuit law. That's important. Um, what else? Well, waves. Since we're talking about waves, we should know what an equation of a wave should look like, right? So, equation of a wave. So essentially, just in this like a constant time multiplied by the sine function or the cos function, with a kx minus omega t inside the sine or the cos function. Lovely. Okay. Oh yes, this obviously this Faraday's law as well. Faraday's law, and it's and I'm hoping that you are more or less acquainted with all of these topics. And if you're not, we'll go slow. We'll not go really quickly across these things. And let's see if you have any problem. You can just ask. Okay, let's introduce this thing. Introduction. Let's start with Faraday's law. Do you remember what Faraday's law said? Okay, so what Faraday was talking about when he essentially gave his very famous law is essentially that if you want to set up an electric field, this is sometimes known as Gauss's law as well. Um, yeah, so yes, so if you want to establish an electric field, E dot dl, this should be equal to whatever the magnetic flux you see. So essentially, electric field is created by a change in magnetic flux, right? So when you're talking about the change in magnetic flux, change in time. So it should be changing in time. So hence there should be a rate of change of time in front of it. And if you would remember, there's this thing called Lenz's law, which essentially tells us that the change in magnetic field, the direction in which it changes, the electric field will be set up in the opposite direction, and hence there will be a negative sign. Yeah. Okay. Faraday's law essentially is just talking about if you have a change in magnetic flux. So you have what is a magnetic or an electric flux? Well, it's just the electric field or the magnetic field in the magnetic flux case multiplied by whatever the area of your loop is. That's it. That's the flux that one is talking about. And if you take the rate of change of that, the time derivative of that, what one would get is something like an electric field. Let's set up a short question on this so that things become a bit more clearer. So let's say there's a magnetic field, phi p. Let's take some value of this to be, let's say, 1 Tesla. Okay. And let's say the area of the loop that you're working with. So here's the loop. There's a magnetic field going across it. Um, so what's the area of the loop? Oh, well, you can consider it to be a circular loop with some radius. Let's call it a meter, 1 meter radius. And yes, okay. Okay. If both of these are constant, what do you expect the electric field to be? If these are the values that are given to you, your phi b, sorry, magnetic field, sorry, not phi b, magnetic field is given to be a Tesla. And let's say you have a radius 1. So both of them are constant. B is constant and area is constant. What do you expect the electric field to be? Di by dt. But that's the point, right? Okay. Di by dt is talking about when magnetic field is produced. So current produces a magnetic field, not an electric field, right? That is what the famous Faraday's experiment was. It was talking about how current essentially produces a magnetic field. Here we're talking about producing electric fields. But electric fields we know are produced by charges. We already know that. But if you don't have a charge, if you have just have changing magnetic fields, can an electric field be established by changing magnetic fields? That's the question. And as it turns out, Faraday's law says yes, it can. It absolutely can. And hence we come to this question. So this d by dt of the magnetic flux. Magnetic flux, is magnetic field multiplied by the area. I've given you a constant magnetic field and a constant radius. So this implies that magnetic field is a constant and the area is also a constant, right? So phi b, which is just b times a, is also a constant, correct? If it's a constant, then if you take the derivative of this, if you take the derivative of this, if you take the derivative of a constant, what happens? Well, the derivative of a constant is just zero because it's not changing. That's the reason why it's called a constant, right? So yeah, so since the change in magnetic field, since magnetic flux is zero, the electric field established by such a system will be zero. Hence, in such a system, your electric field will be zero. But what if I tell you, let's say my magnetic field is not a constant and it's changing. It's changing, let's say B is equal to some constant times X. So let's call this direction X. So the question here is if you have a magnetic field, which looks like a constant times linear variation of X, linear variation of time, sorry. It should be a function of time. Okay, let's start with a function of x so that things become clearer. Let's say it's a function of x. Let's say this direction perpendicular to the loop is the x direction. Let's call it the x direction. What do you think should the electric field established here would should be? See, the magnetic field has only variation in space. It only has variation in the x direction, right? But when we're talking about establishing an electric field, we need variation in time. So when we calculate our flux, which is just the magnetic field times whatever area you have, magnetic field is just Cx and area is just some pi r square, r is just 1. So this is just some pi. So this is Cx times pi. If you take the time derivative of this, well, c is a constant, x is not dependent on time, and pi is obviously a constant, and so hence this implies d phi b by dt should be equal to zero. This implies again the electric field that is established is just zero. Make sense? Okay, if it's clear, then let's slightly change this question again, and then you guys tell me what should be the electric field that is established. Let's say again we consider a loop, the same loop, about a meter in radius. Let's say the electric field looks like some constant multiplied by t squared. Not the electric field, the magnetic field. I'm so sorry. The magnetic field looks like some constant times t squared. T is time. What should be the electric field that is established by inside this loop? So what is your phi b? Yeah, what is your flux of magnetic field? Well, that's just your magnetic field, which is just CT multiplied by, let's not write multiplication sign because X or multiplication sign. How confused about that. So it's CT times the area. Area is just pi because radius is again 1. So this implies d phi p by dt is given to be nothing but c pi, correct? Because d by dt of t is just 1 and constant है, तो all of them will come out of the derivative. Okay, so you get c pi here. You know, this is c pi, so this implies integral, closed integral around the loop of E dot dl should be equal to minus c pi, correct? If that's true, one thing we notice is that so okay, now we need to calculate the left hand side. We need to solve for the left hand side. Right hand side, हमने solve कर. We've solved the right hand side. Right now we need to solve for the left hand side. What does the left hand side look like? E dot dl. Dl is just the circumference of this loop. Well, if dl is just the circumference of the loop, let's just put the value in, right? So we can just write it as E. Mm, you can, so if E dependent on x itself, on distance itself, then you could not have taken this out. But since E is not really dependent on distance, you can consider from the symmetry of the system. So whatever loop you're taking will be dependent on whatever symmetry the system has. In the sense that if there is a charge is kept here, then the symmetry is a spherical symmetry, right? If you increase the radius, so in all directions, on a sphere, you should have the same electric field because there is a spherical symmetry. If you have a rod, then you should have a cylindrical symmetry. So your loops will be will be circles around this thing. So in a cylindrical way. Similarly, here also, it will be, since it's not dependent on time and there's a direction in which there is the magnetic field is given, the symmetry is a cylindrical symmetry. Always think about whatever symmetry, whatever question you're getting. Always think about the symmetries of the question. That will help you a lot. Okay, so E multiplied by the circumference. What's the circumference of this? Well, that's just 2 pi. 2 pi times R, but R is just 1. So it's just 2 pi. You get this as C pi. The pi's cancel out. So this electric field is nothing but C by 2. Faraday's law. So what did we understand from Faraday's law? Oh, we understood that electric field is developed. Oh, okay. Notation time. Notation time. I make this mistake always. Yes, I should have said this before I started. So this line that you see under the E that I'm making is essentially what I represent as my vector. So this thing that people represent as a vector on the top, I just put a line underneath, but it's the same thing. I'll try to actually not do this at all, and I'll try to come back to the usual notation. But this is something that I'm comfortable with. So yeah, I might lapse into going back to this notation. So I'm just letting you know so that beach mein you guys don't get confused like in the middle. So this would be E dot dl. Yes. That's the same thing. I mean, the line that I'm drawing underneath it, it's essentially saying that this is a vector quantity. Um, okay, lovely. So what does this essentially tell us? Well, it tells us that the changing magnetic flux would give rise to an electric field. Okay, this is what Faraday's law is talking about. If we're talking about electromagnetic waves, the obvious question that one can ask is, since it's a wave, and we know of other waves, we know of waves like sound waves, we know waves like water waves. What do these have in common? Well, what these have in common is that there is a medium in which they're traveling, medium to travel. Correct? So, I mean, it's a logical conclusion if you really don't know anything about electromagnetic waves, that electromagnetic waves would require a medium to travel. And that is what the initial hypothesis that people came up with was, that electromagnetic waves indeed need a medium to travel. To travel. And they call this medium the ether. Okay? ETHER. Mm. They call this medium ether. But if there is a medium through which light is traveling, and let's think about it for a second. Let's say this circle is the earth. Okay? And there is this medium all around earth, which is the ether. Now the earth is moving through this ether, right? The earth is, because the earth is going around the sun, and the sun is again going around in the galaxy. So one would expect that the earth is moving through the ether. So if you're and the earth is rotating on its own axis. There is this axis, and there is a rotation across this axis. So it's rotating like this. One would expect that if you measure the speed of light at this point, and you measure the speed of light at this point, since at one point you're moving with the ether, and the other point you're moving against the ether, one should expect that the speed of light, if it's traveling through ether, the speed of light should be different at different points on earth. It's a logical conclusion to make, right? If there is a medium, and if you're moving at different speeds in the medium, because you're on the earth and you're doing the experiment on the earth, and the earth itself is moving through the ether, so you would expect that at different points, since it will depend on the flow of the ether, so it will depend on your own movement through the ether. So the speed of light should be different at different points. And they did this experiment. They did this experiment in 1888, and it was done by two very, very capable people. Their name was Michelson, and the other guy was Morley. I think it was David Michelson and Henry Morley. From these are the surnames. Michelson and Morley. They did this experiment called the Michelson-Morley experiment, where essentially they used the fact that if you have light, then two waves, they form an interference pattern. They form an interference pattern when there is a difference in the path length. For the same wavelength, if the path length is different, then they'll interfere and hence give an interference pattern. So what you can do is essentially you can shoot a beam of light from here, make it pass through like a beam splitter. So essentially, this does is it splits the beam into two. The one goes straight, it hits a mirror here. This goes perpendicular in the perpendicular direction, and it hits a mirror here. You keep two mirrors here, then it comes back. Both of them come back, and they interfere at the center again. And you can, from the interference pattern, if these lengths are exactly the same, you'll see no interference. You'll see only white light. If they're slightly different, you'll start seeing interference patterns again. So what you can do is you can set them exactly right, in the sense that there's just a one white blob there, and you can take this apparatus to different points on earth. If the speed of light were to be different in different directions, so in this direction it would be different, and in this direction would be different, what you would expect is that at different points on earth, this bright spot actually changes into such an interference pattern. That is what you'll expect, because speed is different, so path length would be different. As in, it will take different times for the wave to reach there, and hence they should interfere and give an interference pattern. But that is not what they see. What they see, if you do this experiment anywhere on the planet, and they actually did this experiment in multiple places. They did it in 5 different places, so ranging from Australia to Europe to America to to Asia. They did it literally everywhere, and such experiments have been done later on as well, and it has been verified and re-verified again and again. And what you see is that this bright spot just remains a bright spot; it never changes. What does that mean? It means that there's no change in speed of light. The speed of light is the same everywhere. What does that mean? That means that there should not be anything called ether. So essentially, Michaels and Morley disproved the idea of ether. Yes, yes, yes. But now the obvious question comes: if there is no ether, if Michaels and Morley proved that there is no ether, then how are these electromagnetic waves traveling? There is no medium to travel in. How are there waves that are traveling without a medium? So for such a thing to happen, what you essentially need is a self-working system, right? You need a system that essentially itself is first of all making it go ahead, so essentially travel, but it's not dissipating in the sense that the electric fields and magnetic fields are not dissipating. All the electric fields are being converted into magnetic fields, and all the magnetic fields are converted into the electric field. There's no loss of electric and magnetic fields. You need such a system, and such a system is exactly what we realize is what is called an electromagnetic waves. Electromagnetic electromagnetic wave is a very very special kind of wave. It does not need a medium to travel. Why does it not need a medium to travel? Because it's self-propagating. It's self-working or self-propagating. I think propagating is a better word. Propagating. These waves are self-propagating, and it was not until Maxwell who essentially realized that these waves are actually self-propagating. How did he realize? Through his set of equations. We'll come to the set of equations. Now, one of them we've already seen. That's just the integral E dot dl is equal to minus d by dt of the magnetic flux. That is one of the Maxwell's equation. There are four total. Okay. Now let's move a bit forward. Let's move. We were talking about Faraday's law. Let's talk about the Ampere's circuital law. Circuital. That's an L. Apologies. Ampere's circuital law. Okay. Do you guys remember what Ampere's circuital law says? It's essentially the opposite of what we wrote before. Initially, in Faraday's law, we were talking about E dot dl. Ampere's circuital law is talking about V dot dl. Right? And yeah, obviously you need to have to go through a closed contour, a closed loop, and this is equal to what? Any ideas? Well, what do you need to establish a magnetic field? You need current, right? So it should be dependent. It should be equal to the current. um, there should be a constant here of proportionality constant. Well, we call this constant mu naught. Mu naught, we've already, I hope you've already met the permittivity of space, as it is called. It's the same thing exactly. It has a certain value given in most textbooks. Okay, so essentially, Ampere's circular law is saying that magnetic field is produced. This statement, left hand side says production of magnetic field and this is the source. What is the source of the magnetic field? Well, the source of the magnetic field in this case is the current. So let's see what Mr. Maxwell observed from this equation. What Maxwell tried to do is he tried to think of a loop, of a circuit which essentially has a capacitance and capacitor in the middle, and a voltage which is driving the circuit. Obviously, you need a voltage to drive the circuit. Let's say this is some V naught volt. Let's say this has some capacitance C, blah, 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 blah. Now, let's try to apply this Ampere circuit law for this thing. There's some current that is obviously going across here. So let's try to figure out what the magnetic field at this point is. Okay. So let's for that, what do we do? We need to take a loop which goes around the wire. Okay. Let's say the current that is going on is some I naught. It's constant. So what should be the magnetic field? Please go ahead and tell me what the magnetic field at this point should be. Let's say the radius of this is some small r. Or should be the magnetic field. Put like a couple of minutes on it. Just think about it. It's not that difficult. Exactly the same thing as we did in the Faraday's examples. Interesting question. It will depend on something. It will depend obviously on the current, how much current you're putting in, and it will depend on how far you're looking in. So essentially, it will depend on the radius of whatever loop you're doing. Again, why did we take a circular loop like this? Well, because of cylindrical symmetry. Because we know that the virus is straight, so the kind of symmetry that this system would have will have a cylindrical symmetry, and hence we know that on this loop, everywhere on this loop, the magnetic field should be exactly the same. Why? Because of there's this symmetry. There is this inherent symmetry in the problem. Okay, so tell me, what is this? What is this nonsense? Okay, let's put in the values. B dot dl. I've already said the magnetic field on this whole loop should be a constant. So I can just take this magnetic field outside. And dl is essentially talking about the circumference of the circle. So this is nothing but b times 2 pi r, which is essentially the circumference, should be equal to mu naught I naught. Correct? This implies magnetic field is nothing but mu naught I naught by 2 pi r. Agreed? Now think of a different kind of a loop. Think of a slightly different loop. A loop. So because this is slightly tricky to imagine this loop, but think of this loop. So I'm drawing it here again, so that you get a slightly sideways view of this. It's like something like this, right? Think of it like a sideways view of this, and the initial loop was this thing that is going around here, correct? And this wire is going through. Now think of a loop which, well, let's say it starts at the top where we measured the magnetic field initially. Starts at the top, goes only at the back. It's not coming in front. Going only at the back and stops here. It stops here. Then what it does, it goes straight. It goes straight along the line, and same thing here. It crosses the whole thing through the capacitor and hence completes the loop. So this loop is something like this. It's going back, and all of this is back only, and then here in front, it's closing it. So essentially, there's a wire here. Let's think of this as the wire. First, your first loop was loop around it. Next, what you do? Think of a capacitance which is here. At the end, here is the first thing of the capacitance. Here is the second plate of the capacitance. You start from here, so you're not closing the loop here. You're going ahead, and you're closing the loop here. Okay. By doing that, what happens? By doing that, inside this loop, there is no current. So if I take this loop, this let's call this B1, this new B2, according to the second loop, should be B2 multiplied whatever the circumference of this new humongous loop is, should be equal to zero. This implies the magnetic field at this point should be equal to zero. But hey, I already said that the magnetic field was mu naught I naught by 2 pi r. And it's at the same point. So how can there be two different magnetic fields at the same point? It's an inconsistency, and that is essentially what Mr. Maxwell realized. And yeah, he was troubled by this because it's essentially is saying that there's something missing from this equation. And indeed, there is something missing from this equation. Um, what do you think is missing from this equation here? If you see this equation like this, what this equation is saying there is that magnetic field is produced by the current. Sure, absolutely true. But what if magnetic field is produced by something else as well, apart from the current? Electric field. Not only electric field, but change in electric field, right? Or, as one would say, a change in magnetic flux. That is important. Absolutely. And that is what Mr. Maxwell realized, that this inconsistency can actually be solved by introducing a concept of displacement current. Now, what is this displacement current? Well, it's essentially thinking of, let's say, you're inside the capacitor. Do we remember what the electric field inside the capacitor is? Let's say the electric field is like this. Do we remember what the electric field of the capacitor inside the capacitor is? You guys should have done this. This is what I was talking about during the prerequisites. Capacitance, closed capacitor is zero. The electric field inside a closed. Yeah, I mean, see, if you close capacitor, what do you mean by closed capacitor? You mean that there's a capacitor here and you've connected these two by a wire. That is what it means. Obviously, if there is current in flow, there won't be an electric field. But that's not what I do. I don't have this closed capacitor. It's a capacitor. It's a normal capacitor. It's like two plates with some charges on both plates. What is the electric field that you see? Well, we know that the electric field is given by sigma by epsilon naught. Yes, no? We You should have done this in electrostatics course. It's given by sigma by epsilon naught. Okay, if it's sigma by epsilon naught, so what is sigma? Sigma is essentially the surface density of the charge, right? So sigma is nothing but the total charge divided by the total area. That is what sigma is. It's charge density, so it's charge per unit area. Okay, let's put this. Yes. So let's put this. You get your electric field is nothing but Q by epsilon naught A. Lovely. But what we need to find is the flux, right? So what we need is phi E, the flux of the electric field. And flux we know is given by the electric field multiplied by the area. Flux is given by the electric field multiplied by the area. So what is the electric field again? Epsilon naught A multiplied by the area. The area cancels. What do you get? You get the total charge divided by epsilon naught. Now, what do we need? We need the rate of change of the magnetic flux. So let's talk about the rate of change of magnetic flux. Phi E, well, this should just be equal to 1 by epsilon naught d by dt of q. And what is d by dt of q? Right, d by dt of q is like a current, right? Q is the charge, and the rate of change of charge is just the current. Yes, no, maybe. Moving charges is current, right? So if there is rate of change of charges, you will expect a current to be there. So this term here. Okay, so we were talking about the second term. The second term is just the rate of change of charge. Rate of change of charge is nothing but a current. So this is like a current. It's not exactly a current because no charge is being flown. This Q charge is not like this charge is flowing from one end of the capacitor. So that's not happening. That is absolutely not happening. The charges are there on the capacitor, on the plate of the capacitor. Establishing an electric field, yes. But what essentially this is saying, that it is saying, if we invert all of this, uh, if we if we like invert all of this, what do we get? We get dq by dt is equal to epsilon naught d phi by d phi e by dt. Correct? Okay. So this is essentially some current. So let's call it the ID or displacement current, and we can expand our how do you say the what equation was that, the ampere circuit law, by adding this current to the mix. So essentially by saying that the if I want to establish a magnetic field, dot dl inside a loop, what I need is essentially mu naught times whatever current is passing through the loop plus the displacement current. Okay, so the intuition that Maxwell got was from that circuit and those two loops. If you make, what you realize is that the magnetic field is different. At the same point, the magnetic field is different if you take two different loops. That should not be the case. From there, he realizes that this setup of a capacitor itself can create a magnetic field by inducing this displacement current inside it. So the total current is essentially the current that you're going through the wire plus the displacement current, and displacement current is given by plus epsilon naught d phi e by dt. Lovely, makes sense. Now, where does such a thing exist? Well, such a thing essentially exists. So, what exists in between the plate of the capacitor? Well, generally, if you put something like a conducting, let's say cube, let's say I put a conducting cube here, the whole point of the capacitance is ruined, like absolutely ruined, right? Because then it's just like if I have like a metal sheet, metal cube here, well, then all the current that is coming here will just pass through normally. So there is no capacitance anymore. It's just a wire. It's just a wire. That is all it is. But if I put something else here, if I put something like a dielectric, what would such a dielectric do? Well, then essentially this magnetic flux is established inside this dielectric, this electric flux, and this electric flux has a rate of change, and one can when you take the time derivative and always find the rate of change, and hence you find the displacement current. So this displacement current is essentially established inside a dielectric. Okay, what you have is okay, you have a parallel. Okay, let's do the first part together. um, okay, so whenever you're given such a question, um, what do you what is one supposed to do? Well, first of all, just first thing we should always do is see what the question is. So essentially, and write down in terms of symbols what this question is. So what the A part is asking you, it's asking you for IRMS, correct? And then after you've noted what it's asking, note down what is given is equal to question mark, so you can know that you don't know this term, and what is given is yeah, the radius is given to be 6 centimeters. The capacitance is given to be 100 into 10 raised power minus 12 farad, which is nothing but 10 raised power minus 10 farad, correct? And what else is given? Frequency is given to be 500 radian per second. So everything now is in SI units also. So first thing to do, note down what is asked. Second thing to do, note down what all is given. Third thing to do, to note that all the units are consistent. In the sense, if you're working in SI units, you're working in SI units. If you're working in CDS, you're working in CDS. I will keep that in mind. So, for example, here this is 6 centimeters, not in SI units. So you change it to 6 into 10 to the power minus 2 meters. Lovely. Now you need to calculate the current. Oh, what is current given by? Oh, you're also given the EMF, right? Yeah, 20, 230 volt. You're given the EMF, so essentially the potential difference, and the RMS potential difference. So that's 240 volts. Now, what is one asking you to do? What one is asking you to do is to calculate IRMS. Well, we know that that's just potential is just current into the resistance, right? So current is just the potential VRMS divided by the total resistance. Resistance, or when we have things like capacitor, what do we call it? We call it impedance, right? And what is the impedance um, of a capacitor? XC. This IC is 1 by omega C, correct? We've learned all of these things um, in the AC section of your previous chapters. Okay, so everything is given here, right? You're given epsilon as 240. You're given epsilon as 240. You need to multiply this by omega c. Omega is given to be what, 500? Uh, what is epsilon RMS? That's 240, right? Yes, no, maybe. No, it's 230. Okay, so this is 230. What about omega? 500. Lovely. 500 radians per second. So this is essentially epsilon RMS. So this is 230 divided by, not, it's multiplied because 1 by omega c, this comes up, right? Omega c. This is equal to 230 into 500 multiplied by 10 is 1 minus 10. So what's 23 into 5? I don't know what's 230 divided by 2. That's like 115. 115. And 3 zeros, so into 10 to the power minus 7. So that's 1.15 into 10 to the power minus 5. What? Amperes. Make sense?